Okay, so we talked about the elements. Now let's talk about compounds. Right? Uh, Compounds. In this lesson, we're going to focus on classifying compounds and being able to read and write formulas for compounds. Okay, so one of the things you need to be able to do before you can read and write formulas of compounds is to be able to classify it as either ionic or molecular. An ionic compound is made up of ions. A molecular compound is made up of molecules. Right? So what are ionic compounds? Like I said, they're made up of ions, and typically you'll find these under ordinary conditions as solids. Okay, so you'll have positive ions, cations and anions, that are arranged in a regular repeating pattern called a crystal lattice. Okay, so this is an example, a representation of the crystal lattice for a compound called barium chloride. Okay, you can see that you can't really tell in this particular case. Okay, the green spheres represent chloride ions, and the red brownish looking thing spheres represent barium ions. You can see that you can't really tell which chloride ions goes with which barium ions, right? So there are we say there's no such thing as a barium chloride molecule in the solid. So what we have here is just a collection of ions. These ions are held together in the lattice by what we would call an ionic bonding. That's just electrostatic or Coulombic attractions holding them together. Okay, so typically an ionic compound is a solid at room temperature. It has a very high melting point. It takes a very high temperature to melt an ionic compound. Molecular compounds, on the other hand, are made up of molecules. Okay, and the atoms in the molecules are sharing electrons, are held together by what we call covalent bonds. So here's a representation of a solid. Okay, carbon monoxide solid. A crystal of carbon monoxide, so you have carbon and oxygen right here. Okay, so you can clearly see that the carbon and oxygen together, and then neighboring molecules we say are held together in this particular lattice by what we call intermolecular forces. Okay, and in particular you'll learn later the type of intermolecular forces that are holding these carbon monoxide molecules are called van der Waals forces. So they're a lot weaker than the forces that are holding covalently bonded atoms. Okay. As a result, molecular compounds tend to readily melt and vaporize, especially compounds made up of smaller molecules like carbon monoxide. Under ordinary conditions, you'll find them as gaseous because the attractions between the molecules are relatively weak. Okay. Now, it's also possible for molecules to be not arranged in a regular pattern, and in that case, the solid that you get is what we would call an amorphous solid. If the atoms or molecules are arranged in a regular repeating pattern, that's the most stable way that they can be arranged. In a solid, we have what's called a crystalline solid. So, how can we tell from the name or formula of a compound that we're dealing with an ionic compound or a molecular compound? Well, it's easy to tell because an ionic compound, the formula for an ionic compound, okay, the first symbol that you'll see is that for either a metal or you see an NH4 in the formula, okay? So if the formula starts with NH4, what that means is the compound is ionic, and the positive ion happens to be what we call the ammonium ion. So this polyatomic ion NH4+, that's a very commonly occurring polyatomic ion. You should be familiar with that. You should memorize that formula. Ammonium ion is NH4 with a positive 1 charge. Okay, so if you see a metal in the formula or NH4 in the formula, you're dealing with an ionic compound. Otherwise, you're dealing with a molecular compound. So let's illustrate that. Let's classify the following as ionic or molecular. Sodium sulfide. Well, you see sodium. Okay, so that's a metal. So the first part of the name is the name of a metal. So right away you say that this is ionic. Okay. Carbon disulfide. If you look at carbon disulfide, okay, carbon's right here, Okay, so it's a nonmetal, and you don't see an NH4. It's not ammonium, so this is a molecular compound. Okay. Next one, ammonium. You see the word ammonium in the name, that immediately tells you that that ammonium represents a polyatomic ion with a formula of NH4 with a positive 1 charge. So you know that this compound that has ammonium ions. It has ammonium in the name, so it has ammonium ions. This is an ionic compound. Okay? So that's how you classify based on the name or the formula. You look for symbol or name of a metal at the beginning of the name, or you look for ammonium at the beginning of the name. Okay? So classify the following as ionic or molecular. First one, magnesium hydroxide. Is this ionic or molecular? Is it I or M? How would it be? Answers? Here's magnesium. Okay, very good. It's ionic. How about CH3OH? Is that ionic or molecular? So magnesium hydroxide is ionic. Magnesium is a metal. CH3OH. Is it ionic or molecular? Do you see a metal at the beginning? Carbon. Or do you see NH4 at the beginning of the formula? CH3OH, the beginning of the formula has carbon in it, which is a nonmetal, right? And there's no NH4, so that means it's molecular. And finally, ammonium chloride, is it ionic or molecular? Okay, good. It's ionic. And you know that the positive ions in this particular compound are ammonium ions. So this is ionic. Good. All right, so that's simple enough. Okay, how can you tell if you have if your compound is ionic or molecular just based on properties? Like I said, for ionic compounds, they typically have very high melting points, but molecular compounds can also have high melting points. But if you have something that has a very low melting point, it's a gaseous or liquid under ordinary conditions, chances are it's not an ionic compound. Okay, so ionic compounds are typically solids at room temperature. And one characteristic of ionic compounds is that when you do get them to melt, okay, the movement of the ion, the ability of the ions to move when it's melted allows it to conduct electricity. Okay, so when it turns to a liquid, it conducts electricity. Also, if you can get it to dissolve in water, you mix it with water, you get a solution that also conducts electricity. So we say ionic compounds are strong electrolytes. Let me illustrate that with some animations. If you go to, let's see, this PHET website in Colorado, okay, phet.colorado.edu. You look for salt and sugar solutions in the list of animations that they have. Okay, so go to chemistry, general chemistry, and look for salts. Scroll down, you'll find salt and that's salt and sugar solutions right here. Okay, and then click on that Run Now button, and we'll give you a warning about running it. Just go ahead and run it. It's a safe site to go to. What you'll get is this animation right here. So this is what happens when you put salt in water. First of all, let's check the conductivity of water. Pure water, if I've checked the conductivity, is not going to conduct electricity. See? Okay. Now, if I add some sugar into it, so I'm going to shake some sugar into my water, it will not conduct electricity either. Okay, sugar is made up of molecules. It's a molecular compound. Whereas if I shake salt into it, okay, I'm going to remove all my sugar. I'm going to put some salt into it instead. what happens is if I add some salt into my water, you'll see that the light bulb here starts to come on. Okay, so what I've done is I've made my solution conduct electricity. I made a mixture that conducts electricity. So salt is an example of a strong electrolyte. Okay, here's a picture of what happens at the macroscopic level. What happens when I add sodium chloride is this. Okay, so here your sodium ions are shown in purple, your chloride ions are shown in green. You can see when you put your sodium and your chloride ions and your sodium chloride in water, okay, they're not really paired up. They're not paired up as one purple, one green, one sodium, one chloride. There's 1-to-1 ratio, but you can see they're not really paired up. Okay, they all move about more or less separately. And each one, if you look at it from, if you see how they interact with water, this is what you'll see. If I were to put some sodium chloride in water, this is what happens. The movement of the ions in the water separates the ions from each other, so they're all, we say, separately surrounded by water molecules. So we can say that those ions are separately hydrated. Okay? Whereas what happens if I were to add sucrose? This is a sugar molecule, C12H22O11, so you can see this is a molecular compound. If I were to shake some sucrose, okay, table sugar, into water, you can see that the molecules C12H22O11 remain intact. They don't break up into fragments that are charged. So you still get neutral particles dispersed in your water. Okay, let's look at it from a molecular perspective. I'm going to reset this, and I'm going to add some sucrose molecule, sugar molecules in my water, and you'll notice, okay, the molecules remain intact. Each molecule is surrounded by water molecules. Okay, so that that explains why salt is a good electrical conductor, but sugar is not. Okay. So ionic compounds, when you put them in water, they produce a mixture that conducts electricity, and so we say ionic compounds are strong electrolytes. And this is a YouTube video that explains that also. You can look at that video, and there's the link right there. Just a different one. Okay, so like I said, molecular compounds. Okay, the melting point depends on the size of the molecules. Typically, molecular compounds made up of larger molecules would have a higher melting point, so you may find them as solids at room temperature. But molecular compounds that are made up of small molecules, like carbon dioxide, okay, or carbon monoxide, those are not solids at room temperature. They have a very low melting point. In fact, they have a low boiling point as well, so you find them as gases under ordinary conditions. They are mostly non-electrolytes. Okay, as I've shown you earlier, C12H22O11, that's sucrose. You put that in water, it's a non-electrolyte. It doesn't give you a solution that conducts electricity. There are some exceptions, though. There are some molecular compounds that are weak electrolytes. Those are the acids and bases. So molecular acids and bases are mostly weak electrolytes. So that's a class of compounds that behave as weak electrolytes. Weak electrolytes in the sense that they're not as good as ionic compounds as far as producing a solution that conducts electricity. And the exception are these 6 strong molecular acids. They are called strong molecular acids or strong acids because in water they are completely broken up into ions. So for example, HCl. Pure HCl is a gas. Okay, it's a collection of gases. It's a collection of molecules in a gas. But if you put HCl in water, what happens is the molecules break apart into H plus and chloride. So it breaks apart into ions. So one thing that these acids have in common, okay, you look at the formula of these acids, they all start with H, right? Because one thing they have in common is they produce hydrogen ions in water. So HCl, if you put it in water, it breaks up into H plus. So if you remove an H plus from a molecule, what's left behind has a negative charge. So chloride ion is formed if your hydrogen chloride molecule dissociates in water. Okay. Now, other acids beyond these besides these six, the other acids are what we would call weak electrolytes because they're only partially ionized. Okay, so this process right here, okay, the breakup of a molecule into ions, this is ionization, okay, of a molecule in water. So the process is called ionization. Now, most acids can be represented by something like HX, where X is something, okay? So most acids are only partially ionized, we say. In other words, at any given time, only a small fraction of those acid molecules are broken up into ions, okay? But in the case of strong acids, they are completely ionized. So strong acids, we say, are completely ionized. Whereas most acids, okay, other than those six, are partially ionized. Molecular bases are also partially ionized. So let's do a quick check. Which of these is most likely to be gaseous at room temperature? NaCl, CH4, or C8H18? What would it be? Let's classify this first as to whether they're ionic or molecular. Sodium chloride is ionic, right? CH4 is molecular, C8H18 is molecular. So which one is going to be most likely to be gaseous at room temperature? Okay. Sodium chloride's ionic, so chances are at room temperature this is going to be a solid. In fact, this is your common table salt. Okay? So it's not sodium chloride. So compounds that are most likely to be gases at room temperature are molecular compounds. Well, it's B or C. Which one is it? The smaller molecules tend to be gases. In fact, so the answer is B. Okay? Smaller molecules tend to be gases at room temperature. And the reason for that is the attractions between them tend to be weaker than among larger molecules. So the answer is B. Okay, C8H18 is in fact what you call gasoline. It's a gas, but gas because it's short for gasoline, but it's actually a liquid under room temperature. C8H18 is called octane. It's a compound called octane. That's what you find in gasoline. That's a liquid at room temperature. Okay, so CH4 is methane. That's gaseous at room temperature. So small molecular compounds made up of small molecules tend to be gaseous at room temperature. Okay, so methane CH4 is a gas at room temperature. In fact, that's the major component of what you call natural gas. You use it as fuel. The correct answer there is B. Okay, which of these is not a good electrical conductor? A, liquid sodium chloride. B, solid copper. So here's sodium, here's chlorine, solid copper. Copper is over here. Sodium nitrate, so nitrate, you have nitrogen and oxygen over here. Which one is not a good electrical conductor? Not a good electrical conductor. What do we know about metals? Metals are good electrical conductors, so you can eliminate choice B. Okay. And what does it, so sodium chloride and sodium nitrate are both ionic. What does it take for an ionic compound to conduct electricity? What does it take for an ionic compound to conduct electricity? A compound, so this is solid copper, so metal is a good conductor. Okay. Ionic compounds that are melted in molten form are also good conductors. So the correct answer is C. Right? Okay. Is hydrofluoric acid, HF, a strong or a weak electrolyte? Now, the way to tell here is just to compare it to the list of the 6 strong acids. There are 6 known strong acids. What are they? HCl, HBr, HI, HNO3, H2SO4, and HClO4. Okay, so you have to go back to the previous slide. The 6 strong acids, these are your 6 strong acids. You need to memorize those. HCl, HI, HBr, HNO3, H2SO4, and HClO4. So, it's an acid, so it's at least a weak electrolyte. Okay, it's not one of these 6. So, it's not a strong acid, it's a weak electrolyte. Okay? So, that's HF. All right. So now let's talk about writing formulas by first defining what a formula unit is. The formula of a compound indicates the number of atoms of each kind in a formula unit. Okay? So the formula unit of a molecular compound is 1 molecule. Okay, so the formula of the compound is the same thing as the formula of the molecule. Whereas the formula unit for an ionic compound is the simplest set of cations and anions with a total charge of 0. I believe we covered that earlier. So let's look at an example here. How many H atoms are in one formula unit of propanoic acid? So how many H atoms are in one formula unit of this compound? Well, this compound is a molecular compound. So, if you have one formula unit of this compound, you have one molecule of this compound. How many hydrogen atoms are in one formula unit? Okay, so 6. So there's 3 here, plus 2 there, and there's 1 there. No subscript on the hydrogen means 1. So 3 plus 2 plus 1 gives you 6 hydrogen atoms in one molecule. One molecule of this molecular compound is of one formula unit. Now, how do we explain why the formula of a compound that's made up of calcium and nitride ions is written as Ca3N2? Well, when you write it this way, you're saying that if you have one formula unit, you have 3 calcium ions, okay? And you're showing a subscript of 2 for nitride, so that means you have 2 nitride ions. And you can see your charges add up to 0. So plus 2, plus 2, plus 2, that's a total of plus 6. Negative 3 and negative 3 adds up to negative 6. So that's the simplest combination of ions that has a total charge of 0. That's called one formula unit. So one formula unit of this compound has 3 cations, 3 calcium ions, and 2 anions, 2 nitride ions. Okay, so the formulas of ions, how do you know them? You kind of have to start memorizing them. We covered them in the last lesson on monatomic. When we look at the periodic table, you can predict what the charges are for the monatomic ions. Let's just do a quick review of that. Remember, these are plus 1, right? Group 2A, monatomic ions from those are plus 2. These are mostly transition and post-transition, mostly plus 2, but it can vary from plus 1 to plus 4. Okay, and halogens tend to be monatomic ions from those would have a charge of negative 1. From group 6A, the monatomic ions you get would have a charge of -2. Nitride and phosphide would have a charge of -3. Carbon doesn't tend to form a monatomic ion. Okay? So you need to memorize those. As far as polyatomic ions are concerned, you also have to memorize it. You should have a, okay, this is from my textbook, the one I wrote, but in most textbooks should have a list of common polyatomic ions. The only way to really know those is to memorize them, and the only way to memorize them well is to just apply them, to keep using them. Okay, so what I've done on Free Moodle is I posted an activity, oops, on your Moodle site that you can try. Over here under for your next lab is going to be calorimetry part 2. That's where you determine what's called the heat of fusion of ice. And then after that, your next lab will be aqueous solutions. You're going to make aqueous solutions. And some of the pre-lab activities there gives you a review of the elements in the periodic table, classification of the elements. So that's pre-lab activity 1. Pre-lab activity 2 for that experiment would give you a review of formula reading and writing, and gives you the list of the ions that you need to memorize. Okay, so work on those. So let me pull up that document so you can see. Oops. So if you look at that document, so activity 1 deals with classification of elements as metals, nonmetals, or metalloids. Activity 2, 3, and 4 gives you a drill on classifying compounds as ionic or molecular, and then writing the formula of the compound. Okay. So, and then here's a list of the common polyatomic ions, okay, that you need to be familiar with. All right. So, that's the best way to just know these things, is just to memorize them. And the way to memorize them is to just practice using them. Okay? All right. Here's some things you could, some tips for remembering the names of polyatomic ions. Most of the polyatomic ions you need to worry about are negatively charged. The only ones that are commonly encountered that are positively charged that you find in compounds are the mercury one, or mercurous, which is a pair of mercury with a +2 charge, and ammonium ion. So that should be easy to remember. Just those two common polyatomic ions. Most of the ions you'll encounter are negative ions, and their names end in either ate, ite, or ide. Okay? Now, if the name ends in ate and ide, chances are you're dealing with what's called an oxoanion. So it's one of the elements in that ion, one of the atoms is an oxygen. Okay, so nitrate, for example, is NO3 with a -1 charge. And cyanide is CN with a -1 charge. It's not an oxoanion. It doesn't have an oxygen. Nitrate has an oxygen. So, like I said, the only way to remember these things is to memorize. Okay? Okay, that's good. All right. Here's a tip that you can use to memorize the names of ions, polyatomic ions, with names ending in ate and ite. You just need to memorize those ions whose names end in ate, because the ion whose names end in ite just has one less oxygen. So for example, nitrate is NO3 -1. If you have one less oxygen, same charge, then that's called nitrite. So NO3 negative 1 is nitrate. So if you memorize that, it should be easy to remember that nitrite is NO2 with a negative 1 charge. So if sulfate is SO4 with a negative 2 charge, what's the formula for sulfite? One less oxygen. So instead of 4 oxygens, you're going to have 3 oxygens. So SO3 with a negative 2 charge. Okay? So phosphate is PO4 with a negative 3 charge. What is phosphite? One less oxygen. So instead of PO4, you write PO3, and the same charge is going to be negative 3. How about chlorate? Chlorate is ClO3 with a negative 1 charge. So chlorite would be ClO2 with a negative 1 charge. So one less oxygen, you get the formula for the ion whose name ends in ite. Okay? All right. Here's a good memory aid that I found on the internet that you might find useful for memorizing a few of those that have ions that with names ending in ite. So nitrate, carbonate, these are the most common ones you'll see. And if you look at the quizzes on Moodle, these are the most likely ones you'll encounter. These are my favorites. So you should at least memorize these to begin with. Okay, so carbonate, nitrate. Carbonate is CO3 negative 2. Nitrate is NO3 negative 1. Sulfate is SO4 negative 2. Phosphate is PO4 negative 3. Okay, those are the most common ones. A good way to remember this is to say Nick the camel ate. These are formulas of polyatomic ions that end in ate supper in Phoenix. Why am I writing these words this way? A good way to remember that nitrate has a negative 1, Nick has 1 vowel. Carbonate, camel has 2 vowels. Carbonate has a negative 2 charge. Sulfate has a negative 2 charge. Supper has 2 vowels. Okay. Phosphate has a negative 3 charge. Phoenix has 3 vowels. Okay. The number of oxygens is given by the number of consonants here. So Nick has 1, 2, 3 consonants, NO3. Carbonate has 3 oxygens. Camel has 1, 2, 3 oxygens. Okay. Supper, 4 oxygens. Supper has 4 consonants, S, P, P, and R. And then Phoenix, 4 consonants again, 4 oxygens, P, H, N, and X. Okay, so that's just a good memory aid. So Nick the camel ate supper in Phoenix. All right. If you have an ion with a name that begins with hypo and ends in ite, then it just has 1 less oxygen in the ion whose name doesn't begin with hypo. So for example, chlorite is ClO2 negative 1. If you put hypo in front of the name, hypochlorite, you have 1 less oxygen. It's just ClO negative 1. So bromate is BrO3 negative 1. Bromite would be 1 less oxygen, BrO2 negative 1. And then if you put a hypo in front of the bromite, then it's just BrO negative 1. Okay? Now, if you have 1 additional oxygen, you get perbromate. Perbromate would be BrO4 negative 1. Okay. So that's the last right here. If you put a per in front of the name of an ion that if the name ends in 8 and it begins with per, okay, then that has 1 more oxygen compared to the ion whose name doesn't have the per. So chlorate is ClO3 negative 1. Perchlorate is ClO4 negative 1. So if iodate is IO3 negative 1 is iodate, then periodate would be IO4 with a negative 1 charge. Okay. So the rest of these, I think they're better off. Okay, let's just try a few of these. Okay, but like I said, the way for you to really succeed at this, being able to read and write formulas of compounds, is just practice, practice, practice. Okay. All right. So let's try this question right here. Which of these is a molecular compound? So let's do a review. Molecular compound. Okay. Why is C a popular answer? What do you notice? What happens when you have NH4 in the name? If you have NH4 in the name, then that means the cation is ammonium. So this is an ionic compound. In fact, you should be able to recognize sulfate is SO4 with a -2 charge. So C is ionic. So it's not the correct answer. We're looking for a molecular compound. So how can you tell if it's ionic? You look for a metal or you look for NH4. So A is ionic, right? It's a metal right there, sodium, sodium. So that's ionic. We're looking for a molecular compound. So it's not A either. Okay, so B and D are both molecular, right? Neither one starts with a metal, and neither one has NH4 in it. Which one is the compound? What's a compound? A compound is made up of at least how many elements? 2 elements. So nitrogen is not a compound. N2 is a molecular element. So the compound here is NH3. This compound is called ammonia. Don't confuse that with ammonium. Ammonium, AMMONIUM, okay, is the ion. Okay, in fact, that's what happens when your ammonia molecule picks up a hydrogen ion from an acid. You get ammonium ion. NH3 is ammonia. That's a molecular compound. That's gaseous. Okay, that's a gas. It's made up of small molecules. Under ordinary conditions, it's a gas, and you can smell it. Okay, that's the characteristic smell that you have in your Windex, your window cleaner. A characteristic smell that you get when you spray your Windex, that's ammonia gas, NH3. Okay, so the correct answer is B. All right, let's look at, okay, so we have more of this. Which one is a molecular compound? Phosphorus trichloride. There's phosphorus, chlorine, ammonium chloride, lithium is over here, aluminum's over here, sodium's over here. Sodium, which one's a molecular compound? Okay, so you see lithium, okay, it's a metal, so that's ionic, right? You see sodium, that's a metal, so that's ionic. You see ammonium, that's ionic, so the answer is A. Okay, so let's skip over to uh, the next. There's a few more questions there, but you'll find the answers in you'll find these questions in your homework also. Okay, let's just do one of these. Okay, let's see. uh, Okay, which one of these is an ionic compound? This should be an easy one. A, B, C, or D? Ethyl acetate, sulfuric acid, sodium hydrogen carbonate, or hydrazine. Very good. You see sodium there? Okay, so that means your positive ions are sodium ions with a +1 charge. Okay, sodium hydrogen carbonate is NaHCO3. Okay, that's your common baking soda at home. Okay, that's another name for that is sodium bicarbonate. Sulfuric acid is one of the strong acids. It's H2SO4. It's a molecular compound, although if you put it in water, it gives you hydrogen ions and sulfate ions. The compound itself is molecular. Okay. Ethyl acetate, we haven't even talked about that, so don't worry about that. Hydrazine, we also haven't talked about that, but it should suffice for you to know that if you have a metal in your compound, okay, the name of your compound starts with the metal, then you're dealing with an ionic compound. Hydrazine is N2H4. That's a compound that uses rocket fuel. Oops. Okay. So, all right. Let's see what else we got. All right, which of the following is a solid with a very high melting point and conducts electricity when melted? What are we looking for here? Something that has a very high melting point and conducts electricity when melted. We're looking for A, B, or C. Calcium chloride, carbon tetrachloride, CCl4, or water, H2O. Very good. Water, calcium chloride. We're looking for an ionic compound. And you can tell from the formula that calcium chloride is an ionic compound. Which of these is a strong electrolyte? What are the strong electrolytes? You either look for an ionic compound or you look for a strong acid. Okay? Are any of these ionic? Okay, so that's molecular. That's molecular. That's molecular, but that's an acid. Okay? But HF, if you look at your list of 6 strong acids, HF is not one of them, so that's a weak acid. So the only ionic compound here is potassium hydroxide. So the answer is potassium hydroxide. Okay? Which of these is a strong electrolyte? Again, if you're looking for a strong electrolyte, what are you looking for? You're looking for either an ionic compound or a strong acid. If you look at this list right here, any of these ionic? None of those are ionic. So that's not ionic, that's not ionic, that's an acid, but that's a weak acid. This is a base, okay, so it's not ionic. And this one right here is a strong acid. It's one of your strong acids. So HCl is a strong electrolyte. Okay. A molecule of fructose consists of 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. Well, what's the formula of fructose? Is it C6H12O6, CHO, or CH2O? Right. So 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. So the formula is C6H12O6. Okay? Okay, it's more of that. Which of these is not the formula of the compound represented by the figure above? If blue spheres represent carbon, so this is carbon. Oops. So that's carbon. That's carbon. The white spheres represent hydrogen. So this is hydrogen, 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 hydrogen. And the red sphere is oxygen. So, which of these is not the formula of the compound represented by the figure above? Okay. Correct answer is A. Okay, so this is the correct answer. Why? Because you have two carbons, okay? Two carbons, and you have six hydrogens. Okay, so 1, 2, 4, 5, 6. And you have one oxygen. So C2H6O is a correct formula. CH3, you'll see this grouping quite often. CH3, CH2, and then there's an OH right there. That's another way of representing that. That's a more descriptive way of describing the structure of the molecule. And you can also say C2H5OH, this grouping right here. CH3CH2, that's a common grouping you'll find. It's often abbreviated as C2H5. Okay, that's called an ethyl group. So this compound is called ethanol or ethyl alcohol. Okay, so that's the formula of ethyl alcohol. Right. What's the formula of an ionic compound consisting of calcium ions and chloride ions? Is it CaCl, Ca2Cl, CaCl2, or Ca2Cl2? What's the answer to this one? Calcium has a +2, chloride has a -1. How many of each would you need so that you get a total charge of 0? Very good. You need one of this one, right? And you need two of those. So formula is CaCl2. How about this one? What's the formula of an ionic compound made up of calcium ions, which have a charge of +2, and carbonate ions, which have a charge of -2? That's the simplest combination that will give you a total charge of 0. Okay, so you need one of each. So one calcium and one carbonate. So the correct answer is A. Okay, calcium carbonate. That, by the way, is chalk. And that's the same major component of limestone and pearl. Okay, let's talk about binary compounds now. Okay, binary compounds is a compound. A binary compound is one that's made up of only two elements. So which of these formulas represent a binary compound? Good. HCl, two elements. This has 1, 2, 3 elements, so this would be ternary. This is not a compound, okay? This is an element. This is a ternary compound. And this is a binary compound. Okay? Binary compounds are fairly easy to name, okay? And they're fairly easy to recognize also based on their names, because when you're dealing with a binary compound, okay, to be able to recognize the name of a binary compound, you just have to look for two words, okay? The name of an element must be in the first word, and the name of an element is also in the second word, but only the stem of the name of the elements in the second word. The second word ends in I. And the names may be accompanied by a prefix: di, tri, tetra, penta, hepta, hexa, octa, nona, or deca for one or both words. Okay, so that's how you can recognize just from the name that you're dealing with a binary compound. You see the name of the element in the first word, which may be prefixed, and the stem of the name of another element in the second word, but the ending must be "ide." Okay? So which of the following are binary compounds? Okay, so ethyl, there's no element called ethyl. There's no element called ammonium. Okay, sodium, and then there's a stem of the element phosphorus, but the ending is wrong, so that's not binary. Okay, so binary has to end with "ide." The second word must end in "ide." So, and then there's the name of the first element there, magnesium, and then the stem of the name of the second element, chlorine, is there. So this is binary. Carbon is the name of an element. Chlorine, the stem of the name of chlorine is there. This tetra here is just a prefix, so that's also a binary compound. Oops, sorry. How's I'm still freezing up right now? Okay, I'm going to try to slow down. Disulfur, difluoride. So you see the name of an element in the first name and with the prefix di. The stem of the name of an element in the second word with an ending "ide" and a prefix di. Okay, so that's also a binary compound. Okay. How do you read the name of a binary compound if it's ionic? Then all you really have to do is, first of all, you can easily recognize that a binary compound is ionic if the first element written is that of a metal. Okay? So all you have to do is name the cation, all right, which would just be the name of the metal if it's a main group metal, or if it's a transition metal or post-transition metal, then it may have to be followed by a Roman numeral to indicate what its charge is. Okay, so if it's main group, which belongs to 1A, 2A, or aluminum, you should know what the charge is. 1A is +1, 2A is +2, aluminum is a charge of +3. Otherwise, you have to specify the charge in Roman numeral, and you may have to figure out what the charge is. So just state the name of the cation and then the name of the anion, which is just the name of the nonmetal with the ending of the name changed to "ide." You don't put any prefixes. Let's look at an example here, FeS. How do I know it's ionic? Iron is a metal. So I know the name of the cation is iron, but since this is a transition metal, I have to specify the charge. The question is, what is that charge? I'll have to figure that out. Okay? Now I look at the second element, it's sulfur, so that means that's sulfide. Okay, the anion is sulfide, and sulfide is S with a -2 charge. So if sulfide has a -2 charge, and there's one of iron and one of the sulfide, so the iron must have a charge of +2. I figure out that it's +2 because they should add up to 0. So the name of this compound is iron, Roman numeral 2, sulfide. Okay, so the name is iron, Roman numeral 2, sulfide. So that's how you write the formula of an ionic compound. Okay, there's a few exceptions you need to be alert to. Okay, there's a polyatomic ion called peroxide, which is 2 oxygens with a -2 charge. Superoxide is 2 oxygens with a -1 charge. Okay, 3 oxygens, 3 nitrogens with a -1 charge is called azide ion. Don't confuse this with nitride, which is monatomic, nitrogen with a -3. Yeah, I think this might be a good time to stop. We'll just finish this up next time. All right. So we'll pick up our discussion next time with naming binary compounds. Sorry.